Vectors for calculus. A vector is a quantity that has both a magnitude and a direction. That's the way it's usually talked about in math and physics. But more generally, a vector is simply a list of numbers. We're going to look at vectors both geometrically, that is like graphically, as well as algebraically. And we're going to do some basic vector arithmetic. So let's start with our geometric or graphical vectors. One note that's important, unless there's something in problem that says that you can't do this, but in general, we can move vectors at will as long as we don't change their length, their magnitude, or their orientation, their direction. For example, consider the vectors A and B. And in books, vectors are often bold, but since I can't draw bold, old schools to put a little kind of semi-arrow on top of the vector. Now, what if I wanted to find the vector A plus B? What does that equal? Or what does that look like? Well, to add two vectors, we need to take one vector. It doesn't really matter which one. We're going to leave it alone. And I'll try to draw A like I drew the original, something like this. I'm not looking for perfection. And then we're going to take B and move it. So how are we going to move B? Well, something like this. Notice that A starts here and ends right there. We call this the tail and the tip. So I need to move the start of B, that is the tail of B, to the end of A and kind of attach it. And then the vector A plus B is the vector that goes from the starting point of A to the end point of B, but takes a shortcut across. And let me put that in a different color for us, just like this. That would be the vector A plus B. Well, what if I wanted to find the vector A minus B? What does that equal? I could do something very similar. Let me redraw A for us. I'll draw it down here, try to approximate it well. Now, what does A minus B equal? A minus B is really A plus the negative of my vector B. So what do you think the negative of vector B is? If you said it's B, but going in the opposite direction, you'd be exactly correct. So this would be negative B. So I took my B, and I'll draw negative B over here next to it, and just oriented it parallel, but in the opposite direction. Once again, we can add the vectors by starting at A, ending at negative B, but taking the shortcut across. And that would be the vector A minus B. In general, in Calculus 3, multivariable, we often think of vector addition and subtraction in terms of a parallelogram. So if I have something like this, if I have A, and I'll draw a slightly different B here. If this is A and this is B, then I could finish off the parallelogram by doing this. Something along those lines. I now have a parallelogram where I kind of have A over here and B over here. But then A plus B is one of the diagonals. In fact, A plus B is this diagonal right here. And if you think about it, the other diagonal is A minus B. And if you're unsure, just kind of do an example on your own so you can see that. But I just wanted you to be aware that very often a plus b and a minus b are thought of as diagonals of a parallelogram whose sides are made by the vectors a and b. Okay, what if I wanted to multiply a vector by a constant? So I'll try to redraw my original a like this. What do you think 2a looks like? Well, 2a looks exactly like a, except it's twice as long. There's 1a plus another a. Of course, that gives us 2a. Simple like that. But let's take a look now at an algebraic vector. Because most often when we're dealing with vectors, we're going to be dealing with more of an algebraic side of things. And we'll do some basic arithmetic again, addition, subtraction, and multiplying by a constant. But let's define some things. So let us have two vectors, we'll call them u and v, and they're in three-dimensional space. That's what it means. U and v are elements of the three-dimensional space. And we'll define u to equal the vector x1, y1, z1, vector notation. And v is going to be the vector x2, y2, and z2. So when you see these kind of hard brackets, kind of look like less than, greater than signs, that's one indication that we're dealing with vectors. So what does u plus v equal? Well, when we're adding vectors, we simply add like components, meaning we add the x's together, that's my new x, and then the y's together to get the new y, and then the z's together to get the new z's. What if we want to multiply a vector by a constant? So I'll say k is an element of the reals. That just means k is a constant. Well, you probably figured this out. But if I want to multiply a vector by a constant, I simply multiply each of the components by that constant. It's like we distribute inside. So I have k times u is k times x1, k times y1, and then k times z1. And there's my vector. Let's do a specific example. Let's get out of the general case. So suppose that u is the vector 2, -4, 3, and v will be the vector, say, -1, 0, 5. And a quick note before I go on, the rules that we put down for vector addition and multiplication by a constant hold true regardless of how many dimensions. We're simply going to deal with three-dimensional space more often than not in multivariable. But this is true for two-dimensional and 3, 4, 100-dimensional space. The rules still follow. All right, so back to our example. Suppose that u is given and v is given, and then we want to find the vector 2u minus 3v. Now we could probably do it all at once, but I'm going to do it in parts. I'm going to find 2u first. So 2u says take u and multiply each thing by 2, giving us 4, -8, 6. And then 3v says take each component, multiply it by 3. So I have -3, 0, and 15, like that. And then I'm going to subtract them, which means I'm going to subtract like components. So I'm going to do 4 minus -3, -8 minus 0, and then 6 minus 15. And I get the new vector 7, -8, -9. Let's do a little work on magnitude. What if I wanted to find the magnitude of my vectors? Well, if you watched the first video, I alluded to it. If I want to find the length of a vector, and if I don't have a starting point, we're going to assume that the starting point is the origin. And we point towards that vector. Well, the length of that vector, which we called rho squared, is the three-dimensional or generalized Pythagorean theorem. So the distance, or the length, rho squared, equals the x squared plus the y squared plus the z squared. Just like that. Now, notation for magnitude. I see a lot of new books put magnitude like this, kind of the absolute value, and that's fine. When I learned, we had double bars around our magnitude, so you'll probably see me stick to that standard just because I'm used to it, but a lot of new books kind of use the single bar notation. So if I want to find the magnitude of u, it's simply the square root, right? Because we're trying to find the distance, what we called rho, not distance squared. So the magnitude is the square root of my x squared, so 2 squared plus negative 4 squared plus 3 squared. So the square root of 4 plus 16 plus 9 equals the square root of 29. And let's do the magnitude of v really quickly as well, just to give another example. It is the square root of negative 1 squared plus 0 squared plus 5 squared, or the square root of 26. Let's give a definition of something that you will probably see quite often, and that is something called a unit vector. So a unit vector is a vector that has a magnitude of 1. And you can think of magnitude as length if it helps you out. Some very common unit vectors that you will encounter are the following. We have the unit vector called I, which is a vector 1, 0, 0. And then the unit vector j. And notice we have put like a little hat on top of it. That's actually what we call I hat, j hat. So it's a little bit different. It's not that arrow. But the unit vector j is 0, 1, 0. And then the unit vector k, and these are our standing unit vectors, is the vector 0, 0, 1. So these are the vectors that have a magnitude of 1 in or along the different axes. So this one here, this is the x-axis. This would be the unit vector I. And then in this direction, since this is the y-axis, that would be the unit vector j. And then up the z-axis, that would be the unit vector k. So our standard unit vectors. Note that a vector, which I'll call, in this case, just x, y, z, so u equals x, y, z, could be written like this, and it often is, as x times the unit vector I plus y times the unit vector j plus z times the unit vector k. So when you see these things, this notation, they mean the exact same thing. There's no difference. So we have a unit vector. Very often what we want to do is we want to find a unit vector in the direction of a given vector. So how would we do that? So I'm going to call my vector v. In this case, I'll call it vector v. I'll call this one x, y, z. And my claim is that a unit vector in the direction of v is going to be the vector v divided by the magnitude of v. Or, if I realize that the magnitude is simply a constant, it's some constant times the vector v. So any constant times a vector is parallel. So I know right away it's in the same direction. But what I'm not quite sure of is, how do I know that this vector that I wrote here has a magnitude of 1? Well, let's do just a simple proof. So if I want to find the magnitude of v, well, the magnitude of v is, extended Pythagorean theorem, the square root of x squared plus y squared plus z squared. Now, v over magnitude of v is the vector 1 over x squared plus y squared plus z squared times the vector x, y, z. Let's go back to kind of a general case right here so I can show the algebra a little more simply. So hopefully you can agree this is k times v, right? Some constant times v. And let's find the magnitude of k times v. Well, the magnitude of k times v is the magnitude of well, it's k times x sorry, the computer froze slightly. So kx and then ky and then kz. We'll try to edit that out in post-production. So it's going to be the square root of kx squared plus ky squared plus kz squared, which equals k squared x squared plus k squared y squared plus k squared z squared, all square rooted. And we can factor the k squared out, so we have the square root of And then we'll have k squared times x squared plus y squared plus z squared. And then just a couple more steps in our proof here. Notice that we have the square root of k squared, which is going to be k, and then times the square root of what's left over, x squared plus y squared plus z squared. Now, from up top here, how we define k, we said kv, and then we did a little bit of work. K, in this particular problem, is 1 over the square root of x squared plus y squared plus z squared. And then times this other square root, so square root of x squared plus y squared plus z squared, which gives us a value of 1. So we will be doing some proofs in this class. Many other proofs will involve kind of vector and vector notation. So I want to get you used to doing some of these things. But the big thing out of this last part is that you remember this. The unit vector in the direction v is given by v over the magnitude of v.